In previous lessons, we learned to graph lines. There are other types of functions besides lines, so we're going to learn how to graph a few of these today and then graph other types of functions in the future. So the first one here, we're familiar with absolute value, so this is called our absolute value function. And what we're going to do, we want to graph this, and so whenever we graph something new or unfamiliar to us, it's helpful to just pick a bunch of points and then graph those points and see if we can see a pattern, and sometimes even tell why did the graph turn out that way. So we will choose just some, let's go -3, -2, 1, 0, 1, 2, 3. Seems pretty good. Sometimes you want to choose decimals, but absolute value really doesn't affect decimals any differently than it affects integers. So the absolute value of, remember we're looking for the absolute value of x, so we look, what's the absolute value of 3? Well, that's 3. Absolute value of 2 is 2. -2 is 2. Absolute value of -1 is 1. Absolute value of 0 is 0. And then absolute value of positives are just itself. So we have 7 points we can graph here. So we have the point -3, 3. We have the point -2, 2. -1, 1. 0, 0. 1, 1, 2, 2, 3, 3. And it seems like that pattern would continue. Absolute value of 4 is 4. And so we have this graph. And we can connect these, and the absolute value graph looks like a V, and it passes through the origin. And really, if you look at the right side of the graph, it has a slope. It's a line that has a slope of 1, and the left side of the graph is a line that has a slope of -1. Now, just thinking through this quickly, here's the graph. If we graph this, this whole line here is y equals x, this blue line. So notice the absolute value function looks a lot like it, except that the left side is different. Well, what happened here is all these values are negative, and so when you take the absolute value of negatives, you get positives. So all of those flipped upward over the x-axis to become positive. And so the absolute value function is this black V. Let's take a look at domain and range for this. Get rid of some of these extra things here. Domain and range of absolute value. Well, domain, you can take the absolute value of anything, so the domain is all reals. And then the range, it's real numbers, but we don't have any negatives down here, so we would write the range as y is greater than or equal to 0. An easy way to figure out domain and range, to find the domain, kind of think of collapsing this whole graph on the x-axis. So, or think of what is this graph shadowing? But if we collapsed everything on the x-axis, the whole x-axis would be full of points. Now let's think of range. Range would be collapsing everything on the y-axis. So all these points would collapse on the y-axis. And what part of the y-axis is covered? Well, everything greater than 0 is covered. Nothing down here is covered by our graph. So that's why it's y is greater than or equal to 0. So that's the absolute value function. It looks like a V. Next one looks like this, y equals, and there's brackets around x. So whenever you see y equals brackets around x, it's not just, the brackets aren't just another way of doing parentheses. It specifically means the greatest integer function. Some people call this the floor function. Some people call it always round down function. So rounding, we usually think 5 and greater, you round up. 4 and below, you keep the number the same. But this is going to be always round down. And so we can pick a few points here. Let's -2, -1, 0, 1, and 2. Well, these really don't end up being that helpful. If you round -2 down, you get -2. Like we round to the nearest integer, so these are all just themselves, which is helpful. But we can't just go ahead and graph this and think there's a line here, so because this does look like a line. And so what we're going to have, and these would continue, So now we want to choose some decimals. And so let's pick 0.5. What does 0.5 round down to? Remember, we always round down. It's always floor. We don't ever round up. So 0.5, we're going to go, let's round down to 0. So we have the 0.5, 0. What about 0.75? Well, that rounds down to 0 too, because we always round down. All right, so it looks like everything between 0 and 1 would round down to 0. So between 0 and 1, you would have 0. So we would have a thing here, but what about 1? It's hard to see. Let's change this to blue. At 1, we know 1 rounds to 1. So now we're up at 1. Well, let's say, what about 1.3? Well, round down to 1. So 1.3, we get 1. 1.4, we would get 1. 1.5, 1.7732, we get 1. And so it remains 1, because we always round those numbers down until we get to an x value of 2. So when x is 2, the graph rounding 2 doesn't round, it's just equal to itself. So we have an open circle here. Let's try, these are where some people get mixed up. Let's try negative, let's skip to something else, negative 2.2. Negative 2.2 rounds down. The problem is some people get confused about negative 2.2, and they might put negative 2, but negative 2.2, let's look at a number line. Negative 2.2 is right here. So where does that round down to? That rounds down to negative 3. So at negative 2.2, which is about right here, we're going to be at negative 3. And that will be true for all of that stuff in there. So this graph, now I'll give you another name for it. Some people call this the step function, as you can see why. And so that's, and then this continues, so we can put dots here to show that it continues, because you can't put that an arrow at the end of there. And so there is the greatest integer function. So you have closed circles on all the left sides of those segments and open circles on the right side of those segments. Looking at domain and range, domain, if you collapsed everything on the x-axis, the whole x-axis would be covered, so this would be reals. Well, what if you collapsed everything on the y-axis? Well, only the integers would be covered here. Notice there's nothing in these gaps here, and so the range for this is the integers, and we remember we use a z for integers. The next two are going to be related. This one is y equals 2 to the x. It's called exponential growth, and the way we tell if it's growth is if this number here is greater than 1. So the number that you're taking or has the exponent has to be greater than 1. Then it's called exponential growth, and you'll see why, hopefully shortly, why that's called exponential growth. So let's go ahead and put our x-axis and y-axis here, and we're going to choose some points and see if we can graph them. So let's start, let's do negative 2, negative 1, 0, 1, and 2. 2 to the negative 2. If you remember what negative exponents means, that means we're going to move this to the denominator, and it's going to be a positive exponent. So that's 1 over 4. So we have negative 2, 1/4. And then negative 1, 2 to the negative 1. Well, that's 1 over 2 to the first equals 1/2. 2 to the 0, anything to the 0 power is 1. So when we have 0, we have a 1. 2 to the first is just 2. So when you put 1 in, you get a 2. When you put 2 in, you get 2 squared, which is 4. So when we put 2 in, we have a 4. We can go ahead and put 3 in, see what happens. 3, 2 cubed is 8. So only 3 we have. And we can put 4 in. 2 to the 4th is 16. That's not going to show up on our graph that we have drawn here. Let's go a little bit further back. 2 to the negative 3, that's 1 over 2 cubed, because a negative exponent moves the whole thing to the denominator, makes that exponent positive, so we get 1/8. And so this keeps getting smaller. So 1/8, if you look at a pattern, we have 1/2, 1/4, 1/8, then it would be 1/16. And so the graph of this is going to look something like that. And so that's an exponential growth. An important part of exponential growth when you're doing this, there's always this important point here. I call it an anchor point, but the point 0, 1, because for any exponential function, if you put anything to the 0 power, you're always going to get 1. So you have a 1 there. So we have our anchor point at 0, 1. We have another special thing here. Notice that as we get lower and lower, this thing is never going to touch the x-axis, because even if we put a really small number in there, a really negative number, 2 to the negative 100, we're going to have 1 over 2 to the 100th power. I don't know what that's equal to, but it's very large, but it still isn't negative, and it still isn't 0. So the x-axis is called a horizontal asymptote. So a new word for you. So this asymptote is a line that a graph keeps getting closer and closer to, and it doesn't cross over, or it doesn't reach it. And then a couple other things about this, the domain. If we collapse everything to the x-axis, it will cover the whole x-axis, so the domain is the reals. And then the range, if we collapse everything on the y-axis, well, we get everything above 0. We never do get 0, so we can write y is just greater than 0. Not greater than or equal to, because nothing ever was equal to 0 on that graph, because we have that asymptote there. And then the last one we'll look at hopefully quickly here, we have y equals 1/2 to the x, and this is called decay because this is between, so I'll call this a, is between 0 and 1. And let's choose some values. This one is related to the one we just did because they're both dealing with a 2. So let's go -3, -2, -1, 0, 1, 2, and 3. So when we put a -3, this ends up being 1 over 1/2 cubed, which is 1 over 1/8, which we divide 1 by an 1/8, we get 8. And so we have, let's put our axes in here. We're going to have the point, -3, 8. -3, 8. And then we can put -2 in. So we have 1/2 to the -2. This is going to work similarly. It's going to be 1/2 squared in the denominator, which is 1 over 1/4, which equals 4. And so we have -2, 4. Putting -1, 1/2 to the -1. Again, it's 1/2, and 1 divided by 1/2 is 2. This one's easy because anything to the 0 power is 1. And then what happens here is we have 1/2 to the first, which is 1/2. when we put in a 1, we get a half. When we put in a 2, we get 1/4. When we put in a 3, we would get 1/8. And so it looks a lot like the other one, except it's going the other direction. And again, it goes through the point 1, 0, 0, 1, sorry, 1, 0 is on the graph. It still has that horizontal asymptote. On the x-axis. I do want to mention that's the equation y equals 0. Y equals 0 is the x-axis. And then the domain and range are still the same. Domain is reals, and range has to be greater than 0. And so there's a few new functions. We had the absolute value function, we had the greatest integer function, and then this exponential growth and decay functions. And we'll be working with those more later, but you need to know the basic shape of them and some of these properties that we mentioned, domain and range, and for these exponential ones, their anchor point here and the fact that there is a horizontal asymptote.